All right. Well, welcome, as I said before, to our weekly Urban Water Innovation Systems webinar series. Thanks for joining us, taking time out of your day to learn a little bit more about what's going on with the Urban Water Innovation Network. We're excited to continue the Thrust A seminar series with a presentation from Princeton University's Dr. Elie Bou-Zeid. Our first series, Thrust A, is focused on enhancing our fundamental understanding and characterization of the sustainability of urban water systems by comparing trends in the past with alternative future land and water use, population, and climate scenarios. We just completed Theme A1 presentations, which characterize water supply demand patterns under future socioeconomic scenarios. We're now moving on to Theme A2 to assess the impacts of urban water systems on urban heat islands and the regional climate, as well as the ensuing co-benefits for human health. Later in the series, we will explore Theme A3, which focuses on the effects of climate, population, demographic, and policy changes on hydrologic and ecological processes. Our weekly webinars meet on Thursday at 4 p.m. Eastern Time. Our webinar schedule is also available on the UN website under the Education tab. A couple quick housekeeping items. All participants have entered muted, so please use the question or chat queue to ask any questions as they arise. I'll be tracking the questions throughout the session, and we will answer all of the questions at the end of Elie's presentation. Each webinar is being recorded and will be available on our YouTube channel. A link to the video will be distributed as soon as it's available. Finally, a follow-up survey will be sent out after the last Thrust A webinar on June 15th. Please take a moment to answer the 5 short questions and provide some meaningful feedback so we can continue to improve and create engaging materials. So next week, please join us again for a presentation from Drs. Matt Georgescu and Scott Krayanoff as they discuss methods for projecting future environmental change in urban areas. All right, and with that, I'm excited to introduce Dr. Elie Bou-Zeid, Associate Professor in the Department of Civil and Environmental Engineering at Princeton University. After earning a bachelor's in mechanical engineering and a master's in environmental and water resources engineering at the American University of Beirut, he obtained his PhD in environmental engineering from Johns Hopkins University in 2005. He worked as a postdoctoral researcher at École Polytechnique Fédérale de la Suède, I may have completely butchered that, in Switzerland, then joined Princeton as an associate professor in 2008. His broad research interests are in developing a fundamental understanding and better predictive tools for flow and energy and mass transport in the environment, particularly at the interface between lower atmospheric and the Earth's surface. These advances are then applied to various problems ranging from atmospheric flows over complex urban surfaces and the implication for urban sustainability to wind farm modeling and optimization. And with that, I'm going to turn the controls over to Elie, so bear with us for just a moment while we transition.
Okay, great. So thanks, Sarah. And I should have used the English name of that school now that I realize what I make people go through. So anyway, thanks everyone for coming or for attending. Today my webinar, I structured it really to kind of to not be very structured, but rather to tell you a little bit about all the things we're doing and to maybe foster or try to see common interests or common ways we can work together rather than to give you kind of a structured overview of a specific thing we are working on. So mainly the thrust is about modeling cities, and that of course comes with challenges and opportunities. So I'll take you a little bit through the model development we have done in the past, and then what is left to be done and what we will be doing, what we are currently doing and what we will be doing in the future. So the big theme is that we're trying to understand our interaction with the planet. So we both want to understand how we impact the planet and then how the planet comes back and impacts us. And climate change would be, would be one example. But also the environmental modification in urban area is another clear example of how we can interact with the planet and affect it, basically. So to try to understand this interaction, there are, modeling is one way we can go. But when you try to model these interactions, there are a range of challenges. One of the main challenges is the large range of interacting scales. So, for example, if you want to understand cities or how they're affected by the climate or weather, you typically want to be able to extend your atmospheric models all the way to the top of the troposphere at around 11 kilometers. And if you want to do that, typically you're stuck with a very coarse grid. And while you have large coverage, you basically capture all the weather systems and so on. The coarse grid implies that you have a lot of unresolved physical processes, and also that basically your resolution, your model resolution is insufficient. Climate models, for example, typically run at resolutions that exceed the size of a given city. So to get finer details, sometimes what we try to do is, for example, focus on a given city. So we zoom in, and now we don't want to maybe have a large coverage. We're content with a smaller coverage with the aim of being able to resolve more of the small-scale processes, for example, flow between buildings or radiative exchanges between buildings. So in these cases, what we can do is we can have a finer numerical grid, and now our models can capture more of these small-scale processes, which is all good. And we can use these fine-scale models to develop unresolved physics parameterizations for the coarser models, the weather and climate models. But one of the challenges when you only model a small domain is that basically you need a way of getting the forcing or the boundary conditions for that domain to be realistic. The second challenge that's important is especially in urbanization or in urban area, urbanization drastically increases the heterogeneity of the land surface. Obviously, human intervention, whether it's agriculture or something else that you can see on the right, does that too. But really, urbanization increases heterogeneity to an extreme level. In urban areas, typically you have different surfaces and material properties each meter, and so that's really a level of heterogeneity that's quite drastic, and that also imposes challenges in terms of how to represent this heterogeneity of the surface in atmospheric models that you cannot run at that scale. You basically, with atmospheric models, you're typically stuck to a kilometer by a kilometer, while the surface is varying at much smaller scales. So with these challenges, we try to basically develop models or approaches that can overcome them. One of them is model coupling, as you see in this graph. So you can take a mesoscale or regional model. This is basically a weather forecasting model. And you can nest it with itself or with another model to reach the micro and local scale that you see in the top right panel of the figure. And then within that micro or local scale model, you can also nest a very fine model that is mainly focused on representing the small scale physics that occur in the city. And I'm going to take you through how we do this model coupling a little bit in this webinar. Another approach is not to do kind of an online coupling where all the models are talking to each other, but rather to do an offline coupling. So one way to do it is you run a fine scale model. You, for example, understand how forests exchange heat and moisture with the atmosphere. And then you develop a parameterization for these small scale processes. And then you embed this parameterization in a coarse model where the fine scale flow between buildings or trees cannot be captured. You can do it the other way too. You can run a coarse model and then obtain the boundary condition and force a small scale model with it, but that's not very relevant here, so I will not delve into that. So these are two approaches for online and offline model coupling. So, typically when we think about modeling the city, there are some important physical processes that occur on the land surface on the urban land surface that we need to be able to capture well, and that will dictate what model coupling approach we will end up using. So, for example, cities increase roughness, so that slows airflow. They increase heterogeneity, as I already mentioned. There's a reduction in the albedo, both direct, because, for example, the large asphalt surfaces have a very low albedo, and indirect, because if you look, for example, at a shortwave ray coming down, instead of being absorbed once and being reflected back into the outer space or into the higher atmosphere in a city, it can be reflected from a wall down to the land surface, and then reflected from the land surface to another wall. So there's multiple opportunities for this shortwave ray to be reflected. Also, urbanization modifies the thermal properties, the storage capacity, and thermal effusivity of the surface, and also lead to anthropogenic heat emissions and also anthropogenic water emissions. And one of the main impact of urbanization is also the reduction in vegetation and surface moisture. So these are some of the modifications, and obviously if you want to capture the impact of the city on its microclimate, you need to be able to capture these processes very well. In addition, if you think about mitigation measures, and if you want to model the benefits of a certain mitigation measure, then you also are basically trying to modulate some of these processes. So, for example, if you want to reduce the airflow slow down, you want to use lower buildings. If you want to reduce or mitigate the reduction in the albedo, you need to use more reflective surfaces or more spaced buildings. You could try to modify the thermal properties of the city, or you can try to introduce more green infrastructure in the city, or to reduce anthropogenic heat emissions. So also for mitigation measures, if you want to assess them, you really have to capture these physical processes quite accurately. Another aspect that's important is that urbanization or urban modification of the environment is not happening in vacuum. It's also happening in parallel with the modification resulting from global warming. So we know that cities create an urban heat island. We know they modify precipitation and hydrology. We know they modify the ecology and the biogeochemical cycles. There are parallel impacts from global warming for each of these impacts. So in addition to the heating of the city by the urban heat island, we also know that global warming is going to lead to an increase in the intensity of duration and heat wave. We know that global warming will also modify the hydrology and the ecology and the biogeochemistry. And so at some level, we need to be able to understand how these impacts on temperature, on hydrology, and on ecology and biogeochemistry, we need to know how they interact, whether there will be positive or negative or no feedbacks between them, and how should we deal with the risk and try to mitigate it. So given the need to capture the small-scale physics very accurately, and given the need to address both the urban scale and the much larger scale kind of global warming scale impact that we are having, there is really a strong appeal for using online coupled models that actually are talking to each other. So the small and large scales are talking to each other to be able to capture these complexities. Offline coupled model, where basically you have one-way coupling, don't give you all the benefits and don't have all the same potential that fully coupled models can have. So in that sense, we basically what we are aiming to do in this thrust is to develop fully coupled models for the urban environment and how it interacts with its regional and eventually global climate. So let's go back to some of these physics. So as I told you, the urban land surface modifies the interaction of the surface with the atmosphere significantly. And typically, the way we represent these modifications and the various processes that occur in a city is through what we call an urban canopy model or an urban canyon model. Now, you can think of this as a parameterization of everything that basically from a couple of meters below the surface to 2 times the building height, or let's say to some extent just a little bit above the building height. So we're trying to represent everything that happens across this urban canopy layer. And this is a schematic of how we represent these currently in what we call the Princeton urban canopy models. Canopy model. It's a model that we've been working on for multiple years now. We've developed it way beyond the default UCM that was, for example, used in the weather research and forecasting model. So in this PUCM, we capture all the radiative exchanges. So we model how how shortwave shortwave radiation is reflected and absorbed multiple times. We model how long-wave radiation can be trapped in the canyon. We model how heat can be stored and transferred through walls and through the ground. We model the heterogeneity of the urban landscape, so we can model roofs of different kinds, green, black, white, all together. We can, for example, model a city with 50% green roof and 50% dark roofs. And we can model walls of different types, and most importantly, we can model ground surfaces that are also composed of different materials, asphalt, concrete. I guess I can use my mouse as a pointer. I just realized. So we can basically model asphalt, concrete, and grass surfaces. And recently, we also implemented a representation of trees. Trees in our model can shade the walls and can shade the ground. And they also have a deeper root zones that can uptake water from lower soil levels than grass. In this case, I'm showing some roots, and I'm showing 2 levels of soil. In reality, we have 4 actually. So we have 4 soil levels that we can model. And so I talked about this. We improved the way conduction in solids is simulated. We've done also quite a bit of measurements and model calibration to estimate the properties of these urban materials to the best extent possible using sensor networks. And we've implemented realistic hydrological processes and trees. Just a quick note on the hydrology. So now inside the canyon, we can have vegetation in our framework. And as you see, basically, we have multi-layer. I think we can go only to 4 in our current. No, actually, I'm wrong about that. NOAA goes to 4. In our offline PUCM implementation, we can go to a higher number of layers. So we solved the Richter's equations that you see right here, which basically simulate water storage and flow in unsaturated porous media. And at the surface, we can basically have precipitation, evapotranspiration, and runoff. So this is now implemented inside the soil layers that are inside the canyon. We've also implemented something that's important, which is the fact that impervious surfaces actually are not completely dry. So a lot of the roofs at UMBC campus or on Princeton campus are composed of gravel, and these roofs can actually can become a reservoir that stores a significant layer of water if it rains. Similarly, all other urban materials have some storage capacity. So we model now these kind of impervious storage capacities as a reservoir that is filled by precipitation. And when it's filled, basically, it's the increase in its depth. So this derivative goes to 0 if it's full. And if it's not full, precipitation would increase the storage, and evaporation will decrease the storage until basically, so if it rains, the reservoir can get full, and then eventually evaporation will continue to deplete this reservoir until it's empty, and after that you'll have to wait for the next rainfall event. So this is kind of inside inside a canyon. Now, in addition to that, so now we can use this PUCM to represent urban areas of various densities. We can tell the model if this area is very dense with high buildings or not very dense with low buildings and a lot of vegetation. So we can represent different urban canopies. But also within a single atmospheric model, so typically now you want to couple this PUCM to, or this UCM to an atmospheric model. The atmospheric model, typically we're running it with grid cells of 1 by 1 kilometers. And if you take a grid cell of 1 by 1 kilometer, and that scale is actually, if you look at the figure on the left, that's the 1 by 1 kilometer pixels. Those are the 1 by 1 kilometer pixels. If you typically use that, because heterogeneity in urban areas is so so extreme, you are basically missing a lot of the small scale heterogeneity. But you cannot refine your atmospheric models beyond that because the computational cost will be extreme. So one thing we implemented is what we call the mosaic approach, which is to say that within 1 by 1 kilometer grid cell of the atmospheric model, we can actually model multiple subtiles, or we can model the surface at a much finer scale. We've implemented that. So since in the US, typically we have land use data at 30 by 30 meter scale, we can run the surface model at a 30 by 30 meter resolution, while the atmospheric model is running at a 1 by 1 kilometer resolution. The surface model here being PUCM with embedded with the NOAA land surface model. NOAA land surface model takes care of the land surface that's non-urban. So we've implemented that, and basically with that, what you can do is reconstruct the surface properties such as soil moisture or temperature at a much finer scale than the atmospheric component. So if we ran the surface model at the same resolution as the atmosphere, we would get the picture you have on the left. But when we run it at a finer scale, at the 30 by 30 meter scale, you can reconstruct the land surface properties as you see with a much finer resolution on the right. And now actually on the right, you see Baltimore in the upper left quadrant and DC in the lower right or the center of the figure. And now you can also almost start to see the Erdl and the highways of Baltimore taking shape, while in the Erdl being the urban-rural demarcation line, while in the left figure you basically can hardly make sense of these shapes. So we've implemented PUCM, we've coupled it to WRF, and we've implemented it with a mosaic approach that allows us to gain this higher surface resolution. Now, in addition, another important detail is that PUCM models vegetation inside the canyon, but even for example, within an urban tile, an urban 30 by 30 meter grid cell, sometimes you can have a park that's outside of the canyons, outside of streets, and for that, this can be also modeled separately as a vegetated fraction of the urban tile. So even if a tile is categorized as urban, we can still allow for out of canyon vegetation fraction. So with all these kind of details of the surface, we have now what we believe to be an extremely good surface, urban surface model. I'll show you some of the validation later, but we've done a large range of validation looking at soil moisture, heat fluxes, surface temperature, air temperature, and really the model performs quite well, and it performs much better than, let's say, the default UCM that is in WRF, even though I have to say that some of the UCM capabilities in WRF have been improving in parallel to our efforts. Still, while a lot of these subgrid scale or small scale physics are now resolved with the PUCM framework, there are still some simplifications that we're going to try to get get over or tackle in the current project. First, building geometries are taken as averages over the area. So the mosaic approach helps you a lot with that, because now you only need to assume the building properties are homogeneous over 30 by 30 meters rather than over 1 by 1 kilometer. So that helps, but we're still trying to look at how the variability of building heights influence the urban environment. The very complex turbulent heat and moisture exchanges are parameterized using these resistances. This is kind of currently a very weak point of urban canopy models that we're working on. And currently the subsurface and surface are not coupled. So we assume that the topsoil is uncoupled from the groundwater table. The groundwater table is quite deep. And this can be quite an erroneous assumption, especially, I think, in the East Coast and in many other areas. So now I'm going to start to tell you, this is all kind of, if you want, previous work. Now I'm going to, but I think it's important background. Now I'm going to move into what we are doing now and what we plan to do in the future through this SRN. So one of the main things we're trying to do is to try to overcome some of these limitations. So how do we do that? Actually, sorry, there's still a couple of graphs before I go there. So just to give you a little bit of a framework, so currently the PUCM is mainly the surface model, so I didn't tell you much about the atmospheric component, except that it's resolution. So, and with the atmosphere, we couple PUCM to the weather research and forecasting model, which is the standard model used, for example, by the National Weather Service to forecast our weather. So it's a commonly used model, and the way we run WRF is we run it at multiple resolutions. So we have a large domain D01 that has a coarse resolution that captures synoptic scale systems, and then we refine it to D02 and then eventually to D03. D03 is the one I showed you where we capture Baltimore and Washington. So this is kind of the atmospheric component of the model. Also, just a quick overview of the validation. So in the top left, what we see is MODIS. So this is kind of satellite observations. When we started using this about 5 years ago, the default UCM and WRF would give you this result for surface temperature. This is surface temperature, again, observed from satellites. This is the default UCM. And this is the UCM after we've implemented a lot of these kind of advances or improvements in it. And one of the main aspects was the hydrology. Without capturing the evaporation and the evaporative cooling correctly, you really have no chance of capturing observations well. So as you see that our model matches the pattern much better than the default UCM in WRF. In this case, there was no mosaic and no trees. This is before we implemented mosaic and trees. Since then, we implemented trees, as I mentioned, and trees have an important impact. You have to represent them separately of just grass, because grass can only tap into the soil moisture of the top layer, while trees can tap into much deeper soil, and so they can sustain evaporation for a longer time after your last rainfall. So here I have, these are some observations from Basel, a famous urban field experiment, and you see that, for example, here when we run the model with trees, we end up matching the observations much better than without trees. This is for the sensible heat flux. Trees cool down the city, so they reduce the sensible heat flux. On the other hand, if you look at the latent heat flux, which is evaporation, you see that without trees, the model underestimates the evaporation, even when we had urban grass. With trees, the model can basically approach or gets much closer to observations. Also, the canyon air temperature gets much more realistic when you basically represent trees. And with that, you know, what you could do is and what we did already is to try to think about some mitigation strategies. So we studied the interaction of heat waves with urban heat islands. And you can start asking questions: what would happen if I increase my vegetation? What would happen if I use white roofs to increase the albedo of the city? And basically, we did a study for Baltimore, and without going into much of the detail, we found that basically both have a kind of comparable impact. They both cool the air in the city by about 1 Kelvin. If you take the whole city with kind of the outer, you know, the extents of the suburbs. However, if you only focus on the dense downtown, the cooling is actually larger. The cooling is about 2 Kelvin, both when you convert all of your roofs to green and all of your roofs to white, which is an optimistic scenario, but we wanted to see the full extent of these, of the potential of these mitigation measures. A study that we're actually just submitted yesterday is now looking at what are the benefits of urban heat islands during cold periods. So we tend to always obsess with urban heat islands in the summer, but urban heat islands in the winter can actually be beneficial, especially that if you look at health data, there is a higher mortality associated with cold excursions than with hot excursions, even in relatively mild weather or mild climatic regions. And so given that the urban heat islands shield cities from extreme cold, we wanted to basically see what are these benefits. So this is a plot of observational data, just observations. On the y-axis is the urban heat islands, so the difference between temperature in the city and outside of the city. During the daytime, top graph, and during the nighttime, bottom graph. And this is for a period before the cold wave, during the cold wave, and post-cold wave. You see that all the excursions all these numbers are positive, so urban heat islands is always heating the city and sheltering it from extreme cold. But what's also interesting is during extreme cold, so the blue ones, you see that during cold periods, the urban heat island intensifies, which means the city is a more effective shelter from cold during the coldest period when you have a cold spell than before, which is very good news, because basically that tells you that the health benefits are actually accentuated because of this increased effectiveness of UHI, or increased intensity of UHI during cold periods. Also, you see that during the nighttime, which is the coldest period, where a lot of houses in fuel poverty or pedestrian might suffer from health impacts. During the nighttime, the urban heat island is even larger than during the daytime, and so these are important benefits. Now the problem is when we implemented cool or green roofs in this case, even though green roofs in this case are hardly evaporating because basically it's so cold and the roofs are dry, even when they are completely dry, we saw that actually green roofs, for example, if you look at the nighttime, they reduce the urban heat island. So these are differences between these green and cool roofs relative to the regular or conventional scenario. We see that during the nighttime, the cool roofs are reducing the UHI, so reducing the potential benefits of the UHI in the winter. The cool roofs are not having a big impact during the nighttime because the albedo is not important. However, during the daytime, cool roofs actually have a big negative impact, so they reduce the UHI significantly. I have to specify that these simulations are actually for Chicago. So they reduce the UHI by up to a degree. Green roofs, on the other hand, have a slightly positive impact during the daytime. And the main impact of green roof here is not really the evaporation, but the thermal properties. So green roofs, the way we implement them, tend to have very coarse sand or matrix or soil, and that soil has a very weak or very low thermal inertia, which means it's going to heat up in the day more than the conventional roof, and so it will have a slightly positive impact, but it will not store any energy, and so its impact during the nighttime will be different. So the interesting thing is that these are negative impacts, but also the cool roofs and green roofs here are are having very different impacts compared to summertime, where their impacts were very similar. So what this tells us is that when we design green infrastructure, we really have to be mindful about their wintertime impact, especially in a lot of the colder regions in the United States. We cannot just focus on the summertime. So now I'm going to move on to some of the things again that we are doing to continue to improve the PUCM. So to improve the exchanges or the turbulent parameterization for these resistances, we're doing turbulent resolving simulations, meaning that basically we're simulating flow between buildings. Here I just show a regular array of cube with different spacing between the cubes. We're trying to simulate turbulent flow and heat exchanges between these cubes and the atmosphere. And what we want to do with that eventually is to improve, again, the parameterizations of R. So these simulations fully resolve the turbulent exchanges. And from these fully resolved simulations, we can basically develop parameterization for the resistances that are better than the ones that are existing. This is an instantaneous slice that shows all the turbulence. You can average this in time and get the mean flow, and this is the mean flow. Again, for example, here you see if you have very narrow cavity, the heat is trapped between the buildings and it gets very hot. If you have larger spacing between the building, there's more exchanges and the air is cooler. So basically that has a direct impact on pedestrian comfort. This is kind of, again, I only showed you regular cubes, but there's no reason why we need to do regular cubes. This graph is downtown Baltimore, so we can do realistic canopy and simulate flow and heat transport in real cities. So a preliminary analysis, what we've done is we've compared the resistances that we would compute from LES to the resistances the way they are currently basically parameterized in the UCM. So this black line is the UCM parameterization that is given by this equation. And these are the resistances that you would infer from the LES for the leeward, the windward, and the roof and the ground facets. You see basically that this is almost off by an order of magnitude. That is, the parameterization is almost off by an order of magnitude compared to the LES. And we get away with it because we calibrate the UCM and in the calibration, we offset the error that we get, we offset the error that we get from this low resistance. But when you have a model with kind of errors that are offsetting each other, something has to give. So if you calibrate it to get you the correct surface temperature, you're not going to get the correct heat flux, and vice versa. So a better way of proceeding is to kind of use improved resistances based on these LES, and then calibrate the model correctly. So you are not getting basically just a balance of error in these models. So this is, we've completed kind of the LES simulations, and now we're at a point where we can start looking at how we can improve these resistances. Another important improvement is we would like to couple, so everything I've talked to you so far has to do with how we model the surface outside of the cities and inside the city and couple it to the atmosphere. But I didn't tell you anything about the subsurface. In many cases, when the groundwater table is connected to the surface or connected to the root zone, and when the water table goes up and down, this coupling to the subsurface is extremely important. So with Claire, what we are doing is we want to couple par flow with the simulations that Claire is doing with par flow to the surface and the subsurface to PUCM and to WRF. We started doing that. This is the domain that we're going to start with, Baltimore and DC. First, we're running we're going to run the uncoupled par flow and WRF, and then we're going to start to work on the coupling and see what the benefits of the coupling and what is the impact of surface-subsurface connections in this case. And other projects we have a little bit outside of the SRN, but the results of which will feed back on the SRN, is to investigate what is the effect of rainfall on the surface energy budget and of cities. So we want to understand how fast would rain cool urban pavements. We want to understand what are the implications for the surface energy budget. And we want to understand, once you generate this extremely hot runoff, what are the ecological implications for cities. To do that, we are doing a very fine-scale modeling where we basically have resolutions of 1 millimeter here, of basically rainfall and runoff on a inclined urban pavement. These are all the processes that you have to keep track of. And the student working on this, Hamid Reza, has basically done a lot of work to kind of put all of these processes into a single model. So we've modeled this we've modeled this numerically, and we also did some experiments over the campus of Arizona State University with Jiwa Wang to get some. Again, they have these kind of very nice experimental pavements of concrete. Impervious concrete, impervious asphalt, pervious asphalt, and here you cannot see it actually would be the pervious concrete. So we have 4 different kinds of surfaces, and the initial validation of the model is very promising. This is the green is the model, and the blue are thermocouple measurements of the surface temperature. We see that the model is capturing the rapid cooling of almost 16 degrees within a few seconds. Here, okay, we've generated the rainfall, and here using spray showers, and so we generated a very strong rainfall. But in any case, rainfall will cool the surface very rapidly, will extract heat from the surface and basically advect it with the runoff. And so now we're starting to have confidence in our model, and the next step is to start basically using the model to understand how you can design better urban pavements, and also to build a bulk version of this 2D model. We want to build a 1D version that can actually then be implemented in WRF to simulate how to include the effect of rapid cooling from rainfall into the WRF-PUCM framework. This is currently completely absent, so now when it rains, the surface cools by evaporation, but what we're finding is that the biggest cooling is not by evaporation, is by advection with the runoff. And this, once we implement it into WRF, we're going to study how this rapid cooling and the fact that we can now represent it impact storm development over the city. An outlook of what we are doing now. So we're transferring some of these modeling advances and components to the A2-2 project with Scott and Matei. We've sent them some of the urban canopy model components for them to be able to use them into the kind of future climate simulations they're doing. As I told you, we're investigating the impact of cities during cold wave, and we're investigating also how the influence of surface modification, for example, a park or a green infrastructure, will vary as the spatial extent or scale of this intervention varies. So if you have a small patch of grass, it's going to induce what we call a thermal boundary layer that will be small, and we know basically that the depth of the region of the atmosphere that's modified by the surface typically scale like the horizontal scale of the surface divided by 10. So if you do a 10-meter patch, you're only going to feel its extent up to a meter. And in fact, the extent up to a meter will be very weak, and the extent will be mostly strong in the region which is x over 100. So we want to understand now within the WRF-PUCM framework, when you do green infrastructure interventions and you scale them up, how does the impact scale with the size of the intervention? In the future, what we also would like to do is to implement, as I said, rainfall effect in WRF-PUCM. We want to update turbulence resistances in WRF-PUCM. We want to couple to par flow. We want to also investigate novel interventions. So beyond cool and green roofs, we want to think about retroreflective material. So retroreflective material are materials that instead of reflecting like a mirror, they basically reflect the ray in the same direction it came from. This can be very useful because, for example, if you have a wall, instead of this retroreflective wall reflecting the radiation onto the ground, it will reflect it back into the atmosphere. We're investigating materials that maybe can have variable albedos in the winter and the summer, evaporative wall. This is not PUCM. This actually should be PCM. So PCM is phase-changing materials. So I have a collaborator in the University of Perugia in Italy who works on a lot of these kind of novel material and novel skin surfaces. And I will have a student visiting from there that will start implementing some of these kind of novel ideas in PUCM to see what their impact on cities will be. And also we're going to be working with civil and forest and others on the water energy nexus. On this water energy nexus, I just want to show you some interesting results that actually were just being presented right now by a student who's doing her senior thesis with me. She did a lot of effort, dug into a lot of data to construct the full Sankey diagram of the New York City water energy nexus. You see, for example, that if this is the total water use of New York, this is municipal water that we clean, and actually in New York we don't clean it, but we pump it into buildings. And you see that the surface water abstraction that goes into thermoelectric cooling of power plant is almost 4 times larger than the municipal water use. This is water that we don't treat. We just kind of pump it out of the river, cool with it the power plant, and then dump it back into the river. But you see that kind of the water use associated with energy production is extremely high. This is the so thermoelectric cooling of power plant is the biggest water use for energy. On the other hand, if you look at the biggest energy use for water, this would be basically for wastewater treatment. So this this line, which is not huge, but it's not negligible, is the energy, the electricity that we need to use for wastewater treatment. Now, New York is unique because the Catskill is preserved and it's higher than the city. So New York gets 94% of its municipal water from the Catskill. It doesn't need to filter or clean that water. It doesn't need to pump it. It just takes it and basically gravity drives it into the city. The student constructed a model for this water energy nexus and investigated a few scenarios. I want to highlight this scenario where if the Catskill were to be polluted and if it needed now filtration or pumping into the city, this will basically increase the total embedded electricity from the current 2,800 BTUs. It will almost quadruple it to about 10,000 BTUs, and it will increase the fraction of the electricity that's used for water and wastewater from 1% to almost 4 to 5% in this case. Which one? I guess, yes, these are the numbers you should be looking at. So, and it will increase basically total electricity by from almost 171 trillion BTUs to 178 trillion BTUs. So we're talking about a 4% increase in energy demand of the whole city, which is very non-trivial. Lastly, I want to leave you with this very nice videos that we did about how when you change the shape of the roof from flat, which is here, to tilted, that is here, basically slanted roofs, to round, which is now, how basically the circulation and the pattern on inside the street varies, and how these kind of little decisions that we make can actually have a big impact on air quality and thermal comfort for pedestrians. With that, I'll stop, and if you have any questions, I'll be happy to answer them.
Is higher winter mortality due to car wrecks? Cool or green roofs actually might mitigate against that?
Sorry, can you repeat the question? Is higher winter mortality due to what?
car accidents?
No, no, this is just weather related. So this is weather related. So basically the way they would measure that, and I would actually should defer to some people, but I'll give you my simple understanding. You know, basically they go every day of the year and get mortality data for a whole city. And then they basically plot this mortality data over, you know, versus temperature. And they observe a minimum when the temperature is a pleasant, let's say 70 degrees. And when the temperature goes below 70 degrees or above 70 degrees, they start seeing an increase in the mortality rate that is associated with either basically very hot or very cold conditions. And recent studies that have done this over multiple cities in the whole world observe that actually if you look at like moderate heat or extreme heat or moderate cold or extreme cold, the biggest mortality is related to moderate cold. And that is corrected for, you know, the fact that, you know, you have influenza or something else during moderate cold. But overall, the just temperature-related mortality due to colder periods is higher than the one due to heat periods. And so it's not, you know, car wreck would be potentially, I would assume, not counted because I mean I'm sure they would correct for unrelated deaths and these things, but yeah, because they corrected even for like I said, things like flu or something.
Okay, great. Got a couple more that came in. How is anthropogenic heat represented in PUCM, and how is its impact on urban heat islands compared to that of building materials, urban geometry, etc.?
So that's you know, that's the $1 million question. I think what we should do is leave this question for next week, because Mate and his group in ASU, Scott and others, have been working on this specific question a lot. But the bottom line is, if you know what the if you can tell me what is the anthropogenic heat emission, it's very, very, very easy to put it in PUCM. You just add it as a source of heat in the canyon or on the roof or 50-50 or wherever you want. The challenge there really is to get the right number. There are wide estimates, there are big, big differences. And recently, again, the Arizona State University group published a paper on methods to estimate anthropogenic heat emissions. Now, for Baltimore, we have not included it. For simulations in New York, because it's much higher in New York, we include it. So we get an estimate of urban heat island, of anthropogenic emissions, depending on the urban density. And we add that as a heat source basically in the urban layer.
Okay, a couple more here. Someone is wondering if the Princeton model is available for students to use or modify.
We've given our model. Yes, we would be happy. I mean, we'd be happy to give it, but it's not an easy model. Well, I mean, it's not a simple model. So really, you have to kind of be introduced to it, and we haven't written a user manual for it. So somebody has to kind of initiate those students. If somebody is interested in using it, they can come to Princeton, or actually they can also, there's a very similar version that's being used in ASU by Jiwa Wang, and now potentially by Scott Kryenhoff. So it's better to be introduced to it, but we'd be more than happy to share it.
Okay, great, thank you. And one last final question: does the small-scale urban model affect the larger 1 kilometer scale model in any way?
Oh, absolutely, yeah. So it's always fully coupled. So when you let me go back a little bit here, maybe Alec, it will be clearer. Let me go here actually. So so basically the atmosphere, the development of the atmosphere is very much related to the fluxes of heat and moisture and the drag on the wind that it experiences at the surface. So the way this will play out is that the atmospheric component will give the NOAA PUCM the atmospheric properties. Then NOAA UCM will compute the fluxes from the surface to the atmosphere, and will give these heat and moisture fluxes back to WRF or to the atmospheric component. And so they are again. NOAA is computing the surface properties and the surface fluxes, and WRF is, for example, is computing the atmospheric fluxes and atmospheric properties, and they are talking to each other. So definitely there's a two-way feedback between them.